This is from Nest 2015. The variation of the magnitude of the electric field with radial distance smaller due to a given configuration is depicted in the accompanying figure. The configuration could be thick spherical conducting shell with a point charge at its center, thick spherical dielectric shell with a point charge at its center, conducting sphere with a surface charge, two neutral concentric thin conducting shells with a point charge at the center. How does the curve look? So the curve is resembles this, right? Curve resembles it, or even 1 upon r. Okay, except for this discontinuity here. So here, what do you get to see here? The field is 0. Okay, so there is this abrupt change in the slope, not slope, in the value of the electric field. Okay, and with the value of the electric field, it suddenly becomes 0 for some time, for some space, and then it again starts decreasing. Okay, let us use elimination method to solve this MCQ. Let us first argue why C is not right. Look, if we have a conducting sphere, okay, if we have conducting sphere, then under electrostatic conditions, okay, under electrostatic conditions, what does Gauss law tell? Under electrostatic conditions, Gauss law tells us that E bar inside is 0. Is it clear? E bar inside is 0. So that is definitely not right. Okay, C is not right. Conducting sphere with surface charge. So C is not right. Have you got this point? Okay, now let us go to option A. Okay, let us go to option A. They are saying thick spherical conducting shell with a point charge at its center. Okay, let us argue about A, whether A is right or wrong. Okay, look, we have got thick spherical conducting shell with a point charge at its center. We know that field inside a conducting shell, okay, field inside a conducting shell due to surface charge on it, okay, due to surface charge on it is 0. Please try to understand what I am saying. I am saying field inside a conducting shell due to surface charge on it is 0, and electric field obeys superposition principle. Do you agree? Electric field obeys superposition, correct? So if I want to find out the field inside, which I know is non-zero now, okay, from the graph, I can say that if I have a point charge inside, okay, if I have a point charge inside, then the field will only be due to point charge. So if we consider a configuration like this, okay, suppose I consider a configuration like this. Let us say we have this thick conducting sphere. Okay, let us say we have this thick conducting sphere. Okay, suppose this is our sphere, and inside the sphere we have a charge, a point charge. Okay, so this sphere is definitely going to have a surface charge on it. Okay, this sphere is definitely going to have some surface charge density on it, and then let's say we have this point charge here. Okay, so when it comes to the electric field inside, let's say R1, okay, let us say this is R1, and suppose this is R2, and because they are saying that it is thick, what does thick mean? Thick means R2 minus R1 is significantly greater than 0. It's not 0, so we cannot ignore it. Correct? So let us consider R1 and R2. So in between 0 and R1, the field is entirely due to positive Q. So that is definitely going to be like this. Now, in electrostatic condition, can a conductor have field inside? No. So between R1 and R2, the field will drop to 0. Raise your hands if you have understood this. The field will drop to 0, and then what will happen? Then after R2, it will again follow a decreasing function curve. So which option is correct? Option A is correct. Option A is correct. Now if it were a thick dielectric shell, okay, if it were thick dielectric shell, look, we have seen this in theory that inside a dielectric, because of the lesser mobility of charge carriers, the field inside cannot be fully cancelled out. Okay, cannot be fully cancelled out. So it won't be 0 inside. Right? So this overlap with the x-axis won't be there for thick spherical shell. Okay? Now let's come to option D. Option D says two neutral concentric thin cylindrical shells with a point charge at the center. So see, look, for point D, what will we have? Can anyone think of option D? Two neutral concentric thin conducting shells. Now thin is there, the word thin is there. That means momentarily the field will go to 0. Okay, momentarily the field will go to 0, but not otherwise. Okay, not otherwise. So it will be something like this. Then a removable discontinuity. Again a removable discontinuity like sin x upon x at x equal to 0, and then that journey would continue. Have you understood this?
Yes, sir.
Yes? Okay.